You proposed this thing, it's amazing. And then you don't make it? I didn't. You said you did. And I think it's working on the class because it's by candidate after the or do you know now? And it doesn't work this way Wi-Fi. You have to put the section which is the Wi-Fi network into the firmware. So it's not like I could just connect it to my laptop. Yeah, that's not good. So information that
Good morning, everybody. Today's more review. Today's the last day of review for Exam 2. Exam 2 opened yesterday, closes Friday. When you're ready, just go to the math lab and take it at your convenience. We did some reviewing on Thursday, some yesterday, and we're going to do some more today. Tomorrow, we'll move on to the next section. But anyway, I want to start with number 26. It's the last problem in the review. So let's find the equation of the tangent line at the point 0,3, and it's got this equation here. Notice I put the 3's in red because that is the way it appears on WebAssign, which means that is the number that's randomized. And of course, if this is randomized to a 5, maybe that's also going to be a 5. They'll match up. That's a 7, that's a 7. Yesterday we did one that was similar, but in a way backwards, because yesterday there was one where it said find the equation of the tangent line that was parallel to this other line. So the fact that it was parallel, they were telling us the slope. We didn't know the point. We knew the slope, didn't know the point. This one, we know the point, don't know the slope. Either way, though, of course, what we got to do is find the derivative, because derivative is the slope of the tangent line. So I need to find the derivative of this. To find the derivative of this, I'm going to use the quotient rule, because I've got a fraction. So the quotient rule says low d high, so the bottom, just as it is, times the derivative of the top, minus high d low. The top times the derivative of the bottom. And then all of that over the bottom squared. So the bottom sine plus cosine. All squared. Now for these individual derivatives in the quotient rule there, derivative of 3 is 3 all by itself, so that's 0. It's a constant, so the derivative of that is 0. Sine of x plus cosine of x times 0. Minus 3 times the derivative of sine plus cosine. So we got two terms here. We can do the derivative of each one individually. The nice thing about sine and cosine is the derivative is just the opposite one, but there's a negative sign in there. Derivative of sine is cosine. Derivative of sine is positive cosine. Derivative of cosine is negative. Now, I pointed out the way I keep track of this. The way I keep track of it is I think about the graphs. I know the graph of sine looks like this. Starts at the origin, goes on. So if you think about tangent lines, the derivative right off the bat is going to be a positive number up at about a 45-degree angle. So the slope there is going to be 1, positive 1. So I know it's going to be derivative of sine. Starts off positive, so it's going to be the positive cosine. Whereas cosine, if you think about the graph of cosine, very similar, but it looks like this. It starts at its high point here. So if you think about tangent line, it starts off positive, but as soon as you go to the right a little bit, now it's negative. And it's going down, negative. So derivative of cosine is negative sine, and because the tangent lines are going to have negative slope. Anyway, that's the way I remember that. I don't actually just memorize it. I think about the tangent lines. Anyway, sine of x plus cosine of x times 0 is 0. Anything times 0 is 0. If I distribute this negative 3, makes a minus 3 cosine of x. And then negative 3 times negative sine makes positive 3 sine of x. Sine of x plus cosine of x squared. Here, derivative is, I don't need that 0 at the beginning. 0 minus 3 is negative 3 cosine of x plus 3 sine of x over sine of x plus cosine of x all squared. So that's the formula for the derivative in general. But we need it at this particular point. In particular, the x value is 3. So at x equals 3, the derivative evaluated at x equals 3. Sometimes that notation is used to indicate it's being evaluated at a particular point or number. Plug in, I'm sorry, not 3, 0. The y value is 3, the x value is 0, so at x equals 0. Plug in 0 for the x. Cosine of 0. Sine of 0. Sine of 0 plus cosine of 0 squared. And to evaluate these trig functions at 0, cosine of 0 is 1. You can type that in your calculator if you wanted, or think about the graph at the beginning here, x equals 0 is 1. 3 sine of 0 is 0. You can find and type it in the calculator. Think about the graph of sine at the beginning there, it's 0. Sine of 0, down here, 0 again. Cosine of 0, 1 again. So I have negative 3 times 1, negative 3. 3 times 0 is 0. 0 plus 1 is 1. 1 squared. Negative 3 plus 0 is negative 3. 1 squared is 1. Negative 3. So that's the derivative evaluated at x equals 0. So that means that's the slope of the tangent line. So now I have the slope of the tangent line. I also have this point. That's the M. Go see that point. That's the x1 and y1. So I can plug into the point slope. Y minus y1 equals m x minus x1. So y minus 3 equals negative 3 x minus 0. X minus 0 is x. With negative 3x on that side. Add 3. Y equals negative 3x plus 3. So there's the equation of the tension. A lot of 3's. Not really a coincidence. In fact, you can trace it all the way through. That 3, which actually corresponds to that 3, but that 3 here, that gets to 0. That 3, into those 3's, these, that one's gone though because of the 0. So if you trace it all the way through, that's what ended up in both those positions. Because this one came from the point, this one came from the derivative. So what I'm trying to find out is that's what's randomized. If that's a 5 instead of a 3, if that's a 5 there, it's going to be a 5 there. Probably could tell me what the answer is going to be. Y equals negative 5x plus 5. A 7 is going to be negative 7x plus 7. Again, as I've mentioned many times, nothing wrong with making those observations. In fact, it's perfectly fine. It's actually good because you know what the answer should be. You know what you need to end up with. But don't just write down the answer on your exam. If this problem were on the exam, make sure you do show the derivative, plug it in your numbers, so on and so forth. Anyway, I definitely wanted to do that one. I want to start with that one. And I'll open it up to you guys. Does anybody have one in particular? Yes.
Can you do 19?
19, absolutely. 19. Nineteen says differentiate and find the derivative. Doesn't tell you how to do it. You're allowed to use anything that we've talked about in class. Although trying to use the definition here would be extremely difficult. Three e to the x times square root of x. So first of all, we've got the power rule that tells us how to deal with powers. So whenever you have a radical, you can rewrite that as a power. So the first thing I'm going to do is rewrite that. Instead of square root of x, x to the 1/2 power. Next, to find the derivative of this, I'm going to use the product rule because I have things being multiplied, product. Technically, there's 3 things being multiplied there. There's the 3, there's the e to the x, and there's the x to the 1/2. But instead of thinking of it as 3 things multiplied together, I'm just going to think of it as 2. I'm going to think of it as 3e to the x and x to the 1/2. Because when we have a 3 out front, when we have a constant out front, it just slides through the derivative. So I don't need to think about it as being its own separate function. Just these 2 things being multiplied together. So anyway, now to do the derivative with the product rule. Product rule. Let me make sure I say it the same way that they say it in the book. The first times the derivative of the second. The first times the derivative of the second. Plus the second times the derivative of the first. So there's the product rule. Now to do these individual derivatives in here, I can use the power rule here. The power drops down. Let's subtract 1. 1/2 minus 1. Whoops, I already did that again. Plus x to the 1/2. The derivative here, there's a couple things going on. First, that constant that I'm multiplying by, that 3, it slides through. I'll do this very slowly. 3 slides through. 1/2 minus 1, and doing this very slowly. Rewrite the 1 as 2 over 2 so that they have the same denominator. Finish it up in the next step. And the derivative of e to the x is a very special function because the derivative of e to the x is e to the x. And then if I subtract 1/2 minus 2/2 makes negative 1/2. Technically, I'm done with the derivative. I can do a little bit of algebra here, though. As is often the case, though, there's many correct ways to write the answer. Generally, though, negative exponents are not considered simplified. So if I take this x to the negative 1/2 and I write it in the bottom of a fraction, x to the positive 1/2, I've already got that 2 down there, so I'm moving that x to the negative 1/2 to the bottom. And I just wrote this coefficient in the front. So there's a perfectly good way to write the answer. But there's other ways. Yes?
Would the original there be fine to keep as your answer, or would you prefer us to simplify it?
My personal preference would be to take care of this negative exponent, just because negative exponents are not considered simplified. But the truth be told, WebAssign would count this right. I am going to go a little further, though, because when I look at the answer there, this is not what it's shown. That's not what it's shown. It's shown something a little different. Not necessary, but just in case you're curious, I can do a couple more things. First, because I have this x to the negative 1/2, I could rewrite this. It seems weird to do this, but I could rewrite it as x over x to the 1/2. That x, I did do a lot there. Let me explain this some more. I can think of this as x to the 1/2 times another x to the 1/2 over an x to the 1/2. I see where to do that. With this x to the 1/2, putting one top and bottom, because I'm trying to get that one in the bottom. But then if I put these together, 1/2 plus 1/2 makes x to the 1. This x to the 1 or just x. Again, I'm trying to make the denominator the same as this one over here. If this one has a 2, that one doesn't. So I can force a 2 in that other one by multiplying top and bottom by 2. I'll multiply the top by 2, end up getting 6. 2 down there. Now I have the same denominator. 2x to the 1/2. The numerator, though, those two terms, they have a common factor. They both have an e to the x in them, and they both have coefficients divisible by 3. So I could factor out a 3 e to the x. Be left with 1 plus 2x. over 2x to the 1/2. That's still not the way that it's shown in the answer, because they went back to square root. X to the 1/2 corresponds to square root. So one final step here, I could rewrite this as 1 plus 2x over 2 square root of x. That's acceptable. This is acceptable. Technically, this is acceptable. A lot of times there's more than one correct way to write the answer. Okay, next one. Yes.
Can you do number 7?
7? Absolutely. Number 7. Number 7 says, consider the parabola 8 minus x squared. And it wants us to do two things. Find the slope of the tangent line to the parabola at the point 1, 7. Find the slope of the tangent line one 7. Now, if this number is in red, this 8 here, that's what's going to randomize, vary from person to person. And then both of these are as well. So these could vary from person to person. But the goal is the same. This is just the first part. Part A, find the slope of the tangent line. So slope of tangent line means derivative. And then we need to evaluate it when x is 1. So I need to find the derivative of this. This is the derivative. That parabola 8x minus x squared. I can apply the derivative to each term individually. Derivative of 8x minus derivative of x squared. Yeah, I'm doing this slowly. The constant that I'm multiplying by here, 8, it slides through. Derivative of x. Derivative of x squared. Do anything that derivative of x, excuse me, you can think of that x as x to the 1 power. So we can use the power rule. The 1 drops down, and I subtract 1. Derivative of x squared, power rule there as well, just that it's a 2, a 1. Drop the 2 down and subtract 1. If 1 minus 1 is 0, x to the 0 is 1. Anything to the 0 is 1. 8 times 1 is 8. So I get 8 minus 2x. So the derivative in general is 8 minus 2x. But now I need to evaluate that when x is 1. The derivative evaluated x equals 1. Just plug in 1 for the x. So this formula. I get 6. So So that's the slope of the tangent line. So that's the answer to part A. Part B, then, what's the equation of the tangent line? Find the equation of the tangent line in part A. So what I know is that the slope is 6. I calculated that up here. I know it goes through this point. 1.7. Well, it's got a point in the slope. I can use the point slope formula right down the equation. That minus y minus 7 equals 6 x minus 1. And then to get it in slope intercept form, distribute the 6x minus 6. Add 7 to both sides. That equals 6x plus 1. There's the equation of the tangent. Very good. Next one?
Number 5.
5? Yep. Find the limit. Limit as u approaches infinity. 6u to the 4th plus 7 over u squared minus 3 times 3u squared minus 1. So we had some problems finding limits. In particular, we had one section involving infinity with the limits. Either the limit itself was approaching infinity, or once we tried to evaluate it, it approached infinity. Anyway, as it is, it's indeterminate, because if you imagine u becoming extremely large, the numerator is going to be extremely large. You take a great big number, raise it to the 4th power, that's even bigger, multiply by 6, add 7, real big number. Same in the bottom. You take a big number, square it, real big. Subtract 3, well, that's not going to make much of a difference. It's going to be a great big number. Likewise here, square it, big number times 3, big. Subtract 1, that's not going to make a big difference. Big number times big number, big number. So big number over big number, in other words, infinity over infinity, indeterminate. So it doesn't mean the limit doesn't exist. It just means we can't determine what it is in that form. When you've got polynomials like this, though, there's a little trick we can do. Look at the highest power and multiply top and bottom by 1 over that highest power. Now, the denominator is not multiplied out, though. You could multiply it out, but you don't have to. If you just imagine multiplying it out, you could see you would get a u to the 4th. If you did first terms, you'd have 3u to the 4th. Then if you did it inside and outside, you'd get some u squared. So you did the last term, it wouldn't have a u at all. So the bottom would have a u to the 4th in it. The top's got a u to the 4th. So the highest power is u to the fourth. So the trick to being able to evaluate this one is multiply top and bottom by 1 over u to the fourth. If I distribute at the top, some things will cancel. I'll come back to the denominator, but you can see the u to the fourth here cancels with the u to the fourth there. And I'll come back to the denominator. So I'm just left with 1 times 6 or 6. In that first term. Second term, nothing cancels. I'm left with 7 over u to the fourth. And then when it comes time, I can evaluate this limit now in the numerator. Because 6 is unaffected by the limit. 7 over a great big number, that's going to be really small. That limit is going to be 0. So now I can do the top. But back to the denominator. I didn't multiply this out. Again, you could if you wanted to. It's a perfectly acceptable way to do it. But I'm not going to. I'm going to handle it as it is. I got a u to the fourth here. You can think of that as u squared times another u squared. So I'm going to split this up as 1 over u squared times that first factor. And then another 1 over u squared times that second factor. Just splitting up the u to the fourth to distribute 1 into the first factor and 1 into the other into the second factor. Because if I do that now, got 1 over u squared, u squared, 1 over u squared times 3. I distribute this 1 over u squared. That second factor. And I get some things that cancel. Back up here, these u squareds cancel. So I'm left with 1 minus 3 over u squared. Here, u squared cancels with u squared. 1 times 3 is 3. And then nothing cancels here. I'm just left with 1 over u squared. And now I can do that limit too, because the 1's going to be unaffected by the limit. As u becomes large, 3 over a great big number makes a real small number, so that's going to approach 0. And same for this one. That's going to approach 0. 6 plus 0. And this one approaches 0. 1 minus 0. 3 minus 0. 6 over 1 times 3. 6 over 3, which is 2. So the limit's 2. Usually I only like to show one way to do a problem, but I will show you 2 ways. They're really the same, but if I did decide to multiply out the denominator and then do the same thing, just a slightly different way of doing it. So what I could have done instead, if you like this better, if it makes more sense to you. So I do the FOIL method down here. I get 3 u to the 4th minus u squared inside minus 9 u squared. Then negative 3 times negative 1 makes positive 3. Then I can combine these middle terms to make negative 10 u squared. So I just multiply that to the bottom. But then I proceed as over there. Look at the highest power, which is u to the 4th. Multiply the top and bottom by 1 over u to the 4th. So if I do that, 1 over u to the 4th times 6 u to the 4th. It's 1 over u to the 4th times 7. And the bottom over u to the 4th is 3u to the 4th minus 1 over u to the 4th times 10u squared plus 1 over u to the 4th is 3. Things cancel. U to the 4th, u to the 4th. That's what 1 times 6 are just 6. Nothing cancels there. I can just write it as 1 fraction of 7 over u to the 4th. In the bottom, first term there, u to the 4ths cancel. 3 is 3. Second term, u to the 4th, u squared, so 2 of them cancels those 2. So I'm left with 10 over u squared. Nothing cancels there, but I can just write it as 1 fraction. Now if I do the limit, all of these with u's, in the denominators approach 0. The 6 and the 3, they're unaffected. So they don't have u's in them, but all the others approach 0. So 6 over 3 is 2. 2. 2. Whichever way you like. Really, they're the same, just like multiplying it up. One reason I did that, though, is if you compare to college algebra, in college algebra, they just say ratio of leading coefficients, 6 over 3. If you're trying to find what's called vertical asymptotes, if you look to the right, this graph is going to level out at 6 over 3, ratio of leading coefficients. When the degree is the same, ratio of leading coefficients. So in college algebra, you're doing this, but not in terms of a limit. You're told to do that and not really told why. But this is why. Because what's happening is you're imagining that the variables approaching infinity, which you can't do in the original form, but if you do this little bit of algebra, then you can do. So anyway, that's why it levels off. In terms of a graph, what's happening in the middle might be complicated, but as it keeps going further to the right, as the x, or in this case u, approaches infinity, it's going to level out, in this case, to 2. Anyway, next one. Yes.
This isn't the next question, but would you be able to solve it by factoring out a u to the 4th?
Factor out a u to the 4th, yeah. You would still end up with the kind of the same expression, but yep, that's just a different way of looking at it. And then canceling the one you factored, yep, perfectly fine. So they got another problem? You ready? Time for at least one more. I could pick one, but somebody's got one. I'd rather do that one.
Can you do 14?
Absolutely. 14. Fourteen has a graph, but what they say is this is a graph of the derivative of some other function. Fourteen has a graph. All right, so they got this graph, got a couple pieces here, and they say this is a graph of the derivative of some other function. So this is the graph of the derivative. It's not the graph of the original f function itself, it's the derivative of that. And then they ask a whole bunch of questions. They ask, where is f, the original function, increasing? Where is f increasing? Again, not where this function is, not where this graph is increasing, but the original function. This is the derivative. For a function to be increasing, that means it's going up. But in terms of derivative, what that means is the derivative is positive. The slope of the tangent is positive. That means the graph's going up. So we want to figure out where this is positive. Not where this is increasing, but where it's positive. Where it's positive. So it's positive through here. It has positive values, 0 to 2. Let's see, 0 to 2. So that's not the ordered pair 0, 2. That's the interval 0 to 2. And then 4 to 6, it's positive. And then it's positive from 8 to 9. Again, it's positive above the x-axis, 8 to 9. Where is it decreasing? Actually consider this still part of part A. Where's f decreasing? So for f to be decreasing, that means the original function is going down. Not where this is going down. Where the original function is going down. But in terms of derivative, what that means is the slope of the tangent line would be negative. So the derivative would be negative. So where is this negative? Negative. Where is it in the negative? Down here. It's negative down here. It's in the negative values, 2 to 4. And then also from 6 to 8. 6 to 8. It's down in the negative values. Part B, they asked, where does F have a local maximum? Maximum means highest point compared to stuff around it. So in terms of a regular graph, that means something like that. There's the highest point compared to stuff around it. We don't have the graph of F, we got the graph of the derivative. So what does that mean in terms of derivative? For it to be a local maximum, the derivative has to change from positive to negative. That's what happens at a local maximum. Derivatives change from positive to negative. So we're trying to figure out where does it change from positive to negative. Positive to negative at 2. So there's a local maximum at 2. Here's another place where it changes, but it's the wrong direction. It's changing from negative to positive. Come back to that. Likewise here, it's also changing, but the wrong way. Negative to positive. To be a local maximum, it needs to be positive to the negative. So that's the only place where it does that, positive to negative. But also in this part, they ask about a local minimum. That means lowest point. So in terms of the graph, that would be a local minimum because it's the lowest point. But we don't have the graph of F, we've got the derivative. So what does that mean in terms of derivatives? The derivative would change from negative to positive. Negative on one side, positive on the other. So it changes from negative to positive. So as I look through here, where does it change from negative to positive? There it changes positive to negative, wrong way. But here it changes from negative to positive at 4. Negative values, positive values. So negative to positive. And then right here as well, positive or negative to positive. Part C. Concave up. Where's F? Concave up. Concave up means that it's curving in such a way that the concavity is facing up. If I had a function that looked like that, let's say. Through here, from here to here, it's said to be concave up because it's curving in such a way that it's curving in this direction. So that part of the graph is said to be concave up. Whereas this part, it's curving the other way now. It's curving into that direction. That's said to be concave down. When it's concave up, what's happening in terms of the derivative is that the derivative is getting bigger. If you look at it from left to right here, it keeps getting bigger. And then when it's concave down, the derivative's getting smaller as you move left to right. So concave up, derivative getting bigger. So where's the derivative getting bigger? Where's it increasing? It's getting smaller. And starting here, it's getting bigger. It's getting bigger from 3 to 6. then it's also getting bigger from 6 to 9. Concave down. That means the derivative's getting smaller. It's decreasing, so it's going down right there. 0 to 3. And then that's it. That's the only place it's going down. I accidentally skipped this right here, though. I apologize. I know I'm out of time, but right here it did, with this jump, change from positive to negative. The derivative changed from positive to negative. There was a jump, so it did it very quickly. But what that means in terms of a graph is you got a sharp point. So that would also be a local maximum. So I should have had this there too. I skipped it because I forgot about that jump there. But anyway, that should also be a local maximum. Anyway, I'm out of time for today. These are all worked out and posted in Blackboard in case there's one that you wanted to see that I didn't get to do in class. They're posted under the examples in Blackboard, so you can check that out. Anyway, see you tomorrow, and we'll start the next section.
I have a question.
Yeah.
For a problem like that, how would we work that out on a worksheet?
There's really not a lot to show. If you just make a small statement, something to the effect of how you determine that, like it crosses the x-axis, so just something small like that, that would suffice.
I'm actually curious.
Yeah.
So that's like an exclusive point. The local maximum is still 6.
Right here?
Yes.
Yeah. It's just what that, because this is the derivative, what's happening is it immediately jumps down like that.
Gotcha.
So,
At F, it's a local maximum.
yep,
Okay. But not on F. It's
right,
because
right.
it doesn't exist.
Yep, exactly. Yep.
Last night, arms were it was just like they felt forget about the added weight.
Well, I'm walking.
Yeah.
So we have